Welcome back to Astro Seminar, my friends. It's been a nice summer break, but we're back at it. So we do this most Tuesdays at this time in this room. I think I emailed out most of the people who had confirmed like a couple weeks ago. And if you get that, it's also available on the Visual Institute website. There's like a link to seminars, and it's got the whole list of everybody. Yeah, did anything from today not work well logistically? Like anybody who had meetings or like lunches or anything like that? Okay, so everything worked great, great. So then we can just keep doing this for the rest of the semester. So it's my great pleasure, I guess, today to introduce our first speaker of the year, joining us from that orange school yeah, I'm sure you have a lot of personal loyalty towards the long. Yeah, same. Joining us is Cheng-Han Hsieh, joining us from UT Austin down the road. So he got his PhD at Yale, actually, and now he is a Sagan Fellow at UT Austin. So he's really doing a lot of cool work using ALMA in particular to try to understand kind of how and when planets start to form around forming stars, which is pretty cool. So yeah, do I have any other announcements? Other announcements I should make? Good. Okay, so I will let you take it away. That was definitely my peak introduction. They're only going to get better from here.
Hello, everyone. I'm Cheng-Han Hsieh, and I'm a Sagan Fellow at UT Austin. So today I'll talk about the giant planet formation time window from the observational perspective. So one of the big questions in astronomy is to look for other planets outside our solar system. And over the past decade, with TESS and Kepler, until last week, there are around 5,083 confirmed planets detected. And if you look at the distribution of the planets in terms of orbital period as well as the mass, they can be roughly categorized into 3 different groups: hot Jupiter, cold Jupiter, and super Earths and sub-Neptunes. And here also shows the position of our solar system planets. So you can see all the known planets are located in a different parameter space than our solar system planets. This is because of observational bias. It's still very difficult to detect a low-mass planet at further away from the central star. So with different types of planets start to shows up, one of the big questions is how do they form? So planets form in disk inside molecular clouds. So on the right-hand side shows an image of a molecular cloud. This is an image of Orion. And inside the molecular cloud, there were dense regions known as protostellar cores. So if the protostellar cores have mass greater than the Jeans mass, then it's unstable and it will start to collapse under self-gravity. And because of the conservation of angular momentum, as well as the centrifugal force, it will form a flattened structure known as the protostellar disk around the protostar. So the protostellar disk is the place where the protostar as well as the protoplanets are formed. So these protostellar disks are mostly made up by gas. So it's around 99% is like hydrogen and helium, around like 1% made of dust. And inside this disk, you will have like dust start to settle down to the midplane, and these like dust will coagulate and stick onto each other and form pebbles. And some of them will be turbulently transported and towards the central protostar. So here shows an image of like one example of an edge-on disk. So currently there are 2 groups of models on how planets are formed. So one groups of models is to form the planets from top down, and the other groups of models formed from bottom up. So the top down model, you start with a with a core, and then it collapses under self-gravity for a disk. The massive disk will have spirals feeding the central protostar. And if the mass of the disk is too high, then the disk is unstable. It's gravitationally unstable, and the disk will start to fragment. And the surviving fragment will eventually become gas giants. So this set of models was first proposed in the early 2000s, 1997. And however, with the new observations start to show that the disk fragmentation model is not the dominant process for forming giant planets. First of all, in observations, most of the disks are marginally stable, so we do not see a lot of spirals as well as like a fragmenting disk. And also simulations have started to show if we have like a surviving fragment, it's most likely these surviving fragments will continue to accrete gas around it, and it can quickly grow into proto-binaries. So in around 2014, early 2010s, observations of exoplanets shows that gas planets are more common around metal-rich stars as compared to metal-poor stars. So in the sense of metals, you can think it as like dust. So if there are more dust around, then there's more likely to see giant planets. But this prediction is in contrast with the disk instability models, where if your disk is massive enough over some threshold, and it will form, it will collapse and then form giant planets. So the disk instability model do not predict a mass metallicity correlation. So it is in tension with the observation. So the observation shows that the top-down models are not the dominant mechanism of forming giant planets. So another group of models is the core accretion model. So you form the planets from bottom up. So you start with like a very small dust grains, and these dust grains will coagulate and becomes larger and larger over time, and eventually they will form planetesimals and then accrete into planets. So the overall process is summarized by Drukas et al. In the 2023 review paper. So this is a summary plot. So you start with the micron-sized dust grains. So micron-sized dust grains is the typical size of dust in the ISM. And these dust grains will collide onto each other and stick onto each other, and they will coagulate and slowly grows into millimeter size. That's what we see in disk. And between millimeter size and meter size, these dark dust grains are known as pebbles. So pebbles, they have a Stokes parameter around 1. And inside the disk, inside the protoplanetary disk, for the gas, due to the pressure support, so it will rotating slower at the sub-Chamaeleon velocity. But for dust grains, they don't have pressure support, so they were rotating in Chamaeleon velocity, which is faster than the gas. So the dust grains will experience a headwind, and they will slowly radially drift towards the central protostar. So at size around close to a meter, a lot of these like meter-sized planetesimals can quickly drift towards the central protostar within a few thousand years. So this is a problem known as the meter-size barrier. So people have come up with different solutions to this. One of the solutions is the stream instability. proposed by Andrew Yodin in 2005. So the idea is if you have the dust grains to dust to mass ratio around like 1, so these dust grains can push the gas, and so the gas around the dust grains will be moving in the similar velocity. So this will prevent radial drift. And if the dust grains mass becomes too high, and this will set off like a gravitational collapse, and this will help form much larger planetesimals at around like kilometer size. So these kilometer size planetesimals will continue to accrete pebbles and grow larger and larger. And once they reach the mass around like 10 Earth's mass, and it will start to have runaway growth to accrete gas and quickly form into gas giants. So here shows a simulation cartoon diagram by Roman et al. In 2020 to highlight the whole process. So you start with a very small dust grains at micrometer size. These dust grains calculate for millimeter size dust, and due to the instability, extreme instability, and local gravitational collapse, forming much larger planetesimals with tens to hundreds kilometer size. And these planetesimals will continue to accrete the meter-sized pebbles. And then once it reaches the pebble isolation mass, which is around 10 Earth mass, it will have like runaway growth by accreting gas and form giant planets. So this has been like a well-known and proposed by the series and simulations. But one of the big questions in the field of planet formation is that there is a lack of observational timestamps to tell us at what time planet formation should start, and what time the dust grains should be at what size, and at what time the planet formation process should stop. So while we can have theoretical models or even run simulations and that the sync cell grow, it's very difficult to find observational timestamps to constrain these models. So one of the bottleneck of planet formation is to understand the planetary populations and how do we link formation back to its surrounding disk where the planets are formed. So until recently, in 2014, ALMA released the groundbreaking image of Hsieh et al. This is a protoplanetary disk showing a lot of substructures with rings and gaps. And this is the most updated image from Ian Stevens with 25 hours of ALMA time. These like substructures, rings and gaps, are very important and interesting because the rings correspond to pressure maximum. So there's a regions trapping dust grains. So there are favorable sites for forming protoplanets. And also, if you have a hidden planet inside the disk, a planet can easily curve out rings, gaps, and even the central cavity. So searching for these substructures is very important because they could be hints of the hidden protoplanets, or it could be it could show that the conditions are favorable for planet formation. So it's important to note that the previous studies predominantly target large luminous disk or more evolved disk with ages greater than 1 million years. So mostly class 2 disk. So for example, the Odisha survey by Hsieh et al. 2021, as well as the DSHOP survey by Sean Andrews. So until recently, we start to have surveys to look at the youngest class 01 disk to search for substructures. So the most recent effort was led by Nagashi Ohashi in 2023, they conducted the ALMA large program, the EDIS survey. So they surveyed 20 disks shown on the right. These disks are class 0 and 1, which have age less than 1 million years old. So if you look at these disks, you can see that most of them are pretty smooth. So you don't see much substructures in them. So this could be telling us that maybe substructures are pretty rare early on, or maybe they're harder to find. So these EDIS, if you look at the EDIS samples, some of the disks are edge on, so it's a bit difficult to see substructures. And also they select the disks that are much brighter and larger. So until today, we don't really have a high angle resolution, uniform search of these substructures in the youngest class 01 disk. But studying them is very important because it tells us how early does this substructures form, and as a corollary, how early planet formation begins. So before I talk about how we trace the onset of planet formation, it's important to talk about the evolution of protostellar systems. So for the more evolved stars, we can fit the evolutionary tracks on the HI diagram to know its age. But this is not possible for class 0 and class 1 protostellar systems, because these young systems are very embedded. They're embedded inside the Hsieh envelope, and also the accretion onto the central protostar is very high. So if you just plot it on the HI diagram, the accretion luminosity will dominate. So the protostellar system starts with a stellar core, and once you go over the Jeans mass, it starts to collapse, forming a central protostar with a disk, and also a protostellar outflow in the center. And in the class 0, the early class 0 phase, because the envelope is pretty thick, so if we look at the SED, we only see the envelope, the black body emission from the cold envelope. So as the protostellar system evolve, we can start to see more emission from both the disk and the central star. So the disk will give you emission between 1 to a few hundred micron, and the star emission would peak closer to the optical. So in class 1, when that envelope density decreases, the SET can start to see the infrared access from the disk, as well as the emission, the black body emission from the central star. So the SED will gradually shift towards the shorter wavelengths. And in class 2, the outflow opening angle increases, the density further drops, and you will see more emission from the central star. And in class 3, usually the gas is gone, and you leave with a debris disk, and then a planetary system. So in the classical picture, that most of the substructures are formed between class 1 and class 2, and most of the planet formation occurs in between class 1 and class 2. So later I will show that it's actually much earlier than that. So to trace the evolution of planet systems, we look at the SED changes. And at first, it's peak at the long wavelengths, and we start to see more infrared emission from the disk, as well as the stellar component. So from class 0, class 1, and there's a flat spectrum phase between class 1 and class 2. So to quantify the change in SED, so we use something called as bolometric temperature. So bolometric temperature is not a real temperature. It is a temperature of a black body having the same mean frequency as the observed continuous spectrum. So if you look at SED and imagine you're trying to match a black body curve on top of it, and what would that temperature be? So that's a way for us to quantify the whole SED into one single number. So as the protostellar system evolve, we start to see like a more and more short wavelength emission from the central protostar as well as the disk. So the bolometric temperature will increase over time. So that's how we trace the evolutionary stage. So now introducing our campus survey. So here are our campus team. So me, Hector, Ashwaria, Jaime, Don, Maria Jose, Mike Dalham, and Diego. So we use ALMA, the common large millimeter submeter array, to observe the protostellar disk. So ALMA is an interferometer. It composed of 50 12-meter dish located in the Atacama Desert, 5,000 meters above sea level in Chile. So we use it to survey nearly all the embedded protostars in 7 nearby molecular clouds. Chamaeleon 1, Chamaeleon 2, Ophiuchus, Ophiuchus North, Aquila, corollary Australis, and Serpens. From the Dalham et al. 2015 paper, which is the Spitzer Legacy Survey, the C2D, and the global survey. So we cover nearly the full class 0, 1, flat spectrum sources, and early class 2 sources with bolometric temperature less than 1,900 Kelvin. So in total, we detected 184 disks. So out of the 184 disks, 90 of them has a linear resolution around 15 AU. So here is a comparison of our campus survey with the previous surveys to look for these substructures. So the Odisha high resolution survey and the DSHOP survey, they have an angular resolution, linear resolution around 4 AU. And the EDIS survey has around 7 AU. So their angular resolution is better than our survey, but the sample size is much smaller, on the order of between 10 to 20 disks. So our campus survey, we have slightly lower angular resolution, but we have a much larger sample of 90 disks. And most importantly, the sample is relatively uniform, and we do not select for the largest, brightest disk. We try to sample all of the disk in the start of these 7 molecular clouds. And with this, with this sample, we can start to conduct a statistical search for protostellar disk substructures and use it to determine when we start to see substructures and to infer the onset of planet formation. So here shows some of the substructures detected in our samples. This is ALMA band 6, 1.3 millimeter dust continuum emission. So you can see there's a lot of like rings and gaps and some multiple rings. I align them by age from class 1, flat spectrum sources, to class 2. And the age here is the duration for each class. So from our sample, we found multiple ring systems tend to be larger than the, let's see how to get the, multiple ring systems tend to be larger than the other types of morphology. So, so we don't know whether this is intrinsic properties for multiple ring systems, or this could be an observational bias. That like if for larger disk, we're more likely to see multiple rings. If it's too small, we cannot really resolve them. So there's also, it could be observational bias. That's something we'll look into in the future. And interestingly, we found there seems to be 2 populations of substructures. So one of the type of substructures show a central cavity, and the other type are centrally filled. And we see 2 types of substructures all the way from class 1 to flat spectrum and class 2. And we don't know which type of substructures will evolve into our solar system and what kind of planetary system they will evolve into. And interestingly, if we look at all the multiple ring systems, we found that multiple ring systems tend to be centrally filled. So if you look at all the multiple ring systems, like for example, the HO tau and other multiple ring systems, all of them seems to be centrally filled. You don't see a large central cavity and then have multiple rings around it. This is not something we see. And this is something very interesting and also puzzling. We don't know why, but it might be tied to its formation mechanism. So to study the onset of planet formation, it is important to take into account of the effective resolution. So as shown at Bay et al. 2023, if you look at the disk without substructures in a cross symbol, you can see that majority of the disk without substructures have been observed at low effective angular resolution with less than 3. So if you don't have enough sampling across your disk, you're not going to see substructures. So we take into account the effective resolution and only analyze sources that are great with at least 4 samplings across the disk diameter. And also we take out the adjunct sources because it's very difficult to search for substructures for adjunct disk. So here is one of our major results. So for the bolometric temperature on the x-axis, this is, you can view it as like an age tracer. So it's the smaller class zeros are youngest, and then followed by class 1 and then class 2. So for the bolometric temperature, we adopted the measurement from the EHOPS group, which included the Herschel Space Telescope measurement, but they didn't do the extinction correction for the higher part of the spectrum. So this picture we're seeing is the lower limit for the onset of planet formation. So on the y-axis shows the disk radius and disk mass, and we included data from our campus survey as well as archival data. And the blue one shows the sources with substructures, and the orange one without substructures, and the black cross are disks that are more compact and it's not resolved, is with effective angular resolution less than 4. So have less than 4 beams across the diameter. So from here, we can start to see substructure starts to show up around bolometric temperature of 200 Kelvin. So this is early class 1. So previously, the people think that substructure starts to form between class 1 and class 2 at age around 1 million years old, but actually is much earlier. We start to see substructure around 200 Kelvin in terms of bolometric temperature, which is age around 0.2 to 0.3 million years. And we also look at the bolometric temperature derived by Dalham et al. 2015, the Spitzer C2D survey. So they didn't include this was before the Herschel. So they didn't have the Herschel measurement, but they did the infrared correction for the infrared portion of the SED. So what we're seeing here is the upper limit for the onset of these substructures. So you can see that substructures start to show up around 400 Kelvin. So this corresponds to an age around 0.3 to 0.4 million years. So by looking at the bolometric temperature from both 2 different paper catalogs, we can see the onset of these substructures occurs between 200 and 400 Kelvin in terms of bolometric temperature, which is age between like 0.2 to 0.4 million years. And with this large sample, we can start to look at the substructure detection rate. And again, we start to see the huge rise of substructure detection rate between like 200 and 400 Kelvin. So that's the time when we start to see substructures. And that's the onset of planet formation. And we also look at the linear resolution. It's important to highlight the linear resolution. And if we look at the green points, which are the linear resolution between 1 to 6, which is the highest linear resolution possible with ALMA. If you look at all the green points, after around 300 Kelvin, nearly all of the green points have substructures except one. So that is telling us that by mid class 1, T-ball around 300 Kelvin, majority of the protostellar disks have around like 2 to 3 AU size substructures. And one of the questions, now we know when we start to see substructures, another question is that, are these substructures evolutionary linked? So in the recent paper by Okaijo 2025, and also proposed by Hsieh's group in 2019, they proposed that the substructures we see in protoplanetary disk are all evolutionary linked. They can be explained by having a planet plus the radial drift. So just like star formation, there's class 0, class 1, class 2, and class 3. They divide the substructures into 5 different stages. So stage 1, stage 2, 3, 4, 5, with stage 5 being the most evolved. So with our ALMA data, we want to test to see whether substructures follow evolutionary sequence like this, and are they all evolutionary linked? So it's very difficult to try to categorize observations into 5 different stages. We'll be arguing whether this disk belongs to stage 2 or 4. But so we look at the most prominent features for these 5 different stages. And that feature is, if you look at the early stages, there's always centrally filled. And if you look at the most evolved ones, it has a large central cavity. So we divide our samples into like a simple binary classification scheme, like the C type with a cavity type, and the F type, which is field type. So the idea is this: if all the substructures follow the one evolutionary sequence, then we should see early on when T-ball is small, then all of them should be like mostly dominated by the field type. And as it evolves, we should see more disk with a huge cavity in the center. So if they're all evolutionary linked. So here shows the same plot, but with the green showing the field type and the blue circle showing the one with a cavity. As you can see, they're pretty mixed together. And I also calculate the number of disk with a central cavity, the fraction of disk with a central cavity, as a function of bolometric temperature, which is the evolutionary age tracker. And you can see it's pretty flat. We do not see like a strong trend, evolving trend. So this is telling us that protostellar disk substructures that we see are not necessarily evolutionary linked. There could be different populations of substructures generated by different mechanisms in the sample, or if they're evolutionary linked, then instead of finding like a well-organized, coherent like sequence, like protostars, class 0, class 1, class 2, this tells us that the substructures can evolve rapidly and can be triggered at different times. So that's from the analysis we found they are not necessarily evolutionary linked. And it's important to highlight that we start to see the onset of these substructures because we have like good enough linear resolution around 15 AU. But if we go lower the linear resolution, this is at 40 AU resolution, then you don't see much. Then this is what we see by combining the Van Den survey as well as the Serpens Aquila disk in our campus survey. And you can see that most of the disks do not have substructures, with some of them have substructures, but those with substructures are actually pretty large. The rings and cavities are greater than 50 AU. So instead of generating by planets, it's most likely the substructures correspond to the early formation of proto-binaries. So the linear resolution is the key. And also, it's important to point out when the disks are pretty young, it could be optically thick. So we did a quick estimate calculating the brightness temperature using the full Planck function, as well as the dust temperature from Tobin's paper to estimate the optical depth. And while this is an indirect way to estimate the optical depth, we do see there's a trend showing that for the early disk, there is more optically thick. So this is telling us that what we're finding for the onset of these substructures can actually happen much earlier. It is only like a limit. And so this is also making it even more interesting because in the early class 1 phase, the protostars is still forming accreting mass from surroundings. And if the planet formation can start at the same time, then that's telling us the planet and star formation are not isolated. They're actually forming and evolving at the same time since early class 1.
Ask how that reconciles with the lack of the trend for the fraction that have a central detection. I would have figured like if the opacity is high, it's because there is material that's filling the central part.
Well, if when there's a central cavity, so those in their models they think that those are when planets form, it will start to curve out like rings and gaps, and if the rings and gaps become too deep, then it will reduce the amount of dust passing through the gap, and over time the central cavity will start to form. So this is about like the cavity, the central cavity. But when you have early on, let's say if you have some rings, but if the disk is too optically thick, then those like features can be smoothed out because these gaps might be shallow, might not be like completely cleared.
So it's not so much that it's the disk material that's causing the opacity that's like on such small scales around the protostar that's like totally disconnected from.
Yeah, so early on, the substructures are also expected to be smaller as well. They're smaller and there should be shallower. And if your disk mass is also higher and with higher temperature, then the signal can be like washed away. And it's important to note that our sample is complete for disk mass greater than 0.01 solar mass, which is around like around the minimum mass solar nebula, the minimum mass needed to form our solar system. So we don't know what is going on in the compact low mass disk, so which is around like half of the sample. So in these disks, because their mass are too low, so it's more probable that these disks are forming, instead of a Jupiter, they're forming like a Neptunes or other like icy planets or rocky planets. So it would be interesting in the future to investigate whether the low mass compact disks have substructures and how do they evolve, and to see is it different from the higher mass disk, which is expecting to be forming giant planets. So the early onset of these substructures at around like 0.2 million years is also consistent with the CAI storage problem. It could be a natural explanation for the CAI storage problem. So CAI storage problem is a well-known problem in the solar system community. So the idea is this: you have calcium, aluminum, titanium. They form in high temperature near the sun. And they usually have size around like millimeter and centimeters. So all of them should just like spirals in towards the sun and then get engulfed by our sun. And you should not be able to see them. But no, not only we still find them in meteorites, we find them in meteorites that are further away from the sun, in carbonous chondrites. So the question is why? How can we have them surviving and also found in like chondrites? So one possible solution was proposed by Stephen Dash in 2018 in Arizona State University. So the solution is that having a Jupiter's core formed at 3 AU around like 0.6 million years and open a gap. So once you open a gap, and the CAIs outside the Jupiter would be like trapped, and they will slowly like get incorporated into a carbonous chondrite. So our observations, disk observations from ALMA show the substructures like gaps and rings can form around 0.2 to 0.4 million years is consistent with this picture and could be a natural solution to the CAI problem. So I talk about the onset of planet formation, but what are other observational time constraints? When do like planet formation ends? So one possible constraint is like the disk dissipation, but we actually have a better one that is even before the disk dissipates. So this is something very interesting. The answer. The observations actually lies in our sun. So our sun has a metallicity gradient from the core to the surface. And this is known as the solar modeling problem because the signal we got from the sun is extremely good. We have extremely high signal to noise ratio data. So in order to produce the spectroscopic, helioseismic, and neutrino constraints consistently using the solar evolution models is extremely difficult. And models are able to produce all of them consistently. And especially because there is a metallicity gradient from comparing the core to the surface. So our sun has a metal-rich core and a metal-poor surface. So one possible solution was proposed by Kimoto et al. In 2022. So they suggest the metallicity gradient of our sun can be explained by planet formation, so which affects the sun's accretion history. So at first, our sun will accrete materials from the disk, with a lot of them being dust. So this is the high metallicity accretion. And when we start to have planet formations, like when you start to have like protoplanets forming, and these will curve out like gaps and rings, and this will prevent the dust grains from going through these like gaps. So the majority of the mass accreted onto our protosun will be gas dominated. So this will change the metallicity of the accretion. So this will help build lower metallicity like surface. So they did the modeling based on our solar system, and the planet formation process of our solar system leads to the last 4% of the young sun's total mass being metal poor. So this is around like 2.2 million years. So this is also telling us like around like 2.2 million years, the planet should form and have a size that is big enough that can block the dust from accreting onto our central sun. So here is my conclusion. So we conduct the ALMA survey of nearly auto-embedded protostellar disk, class 0 and 1 protostellar disk, and we found at around 0.2 to 0.4 million years with T-ball 200 to 400 Kelvin, which is in early class 1, that substructures are formed during that time. And this is much earlier than what people usually believe, between like class 1 and class 2. So planet formation can actually start much earlier on. And in the early class 1, this is the time when the accretion rate onto the central protostar is still very high. So you're basically the protoplanets and protostars are growing and evolving at the same time in early class 1. And this is only like an upper limit, because even the earlier time, the disk could be optically thick. So there could be smaller substructures that are hidden. So planet formation actually starts pretty early. And we found disks with multiple ring systems are generally larger than the other types of substructures, but this could be an observational bias. And we found, we classified this into 2 different populations, with the central cavity and without a central cavity. And multiple ring systems tend to be centric field. And by looking at the rate of the disk with the central cavity evolve, we found that these substructures are not necessarily evolutionary linked. They could be formed by different mechanisms with different subpopulations, or if they're evolutionary linked, they can be like triggered and evolve very rapidly. And before I end my talk, I want to advertise a conference. So I'm one of the main organizers for the 2025 Star and Planet Formation Conference in the Southwest. So this conference will be at UT Austin, and December 9th to 11th. The abstract deadline is September 1st, but we will push it extended. And this is a free conference. So we got fundings from the Los Alamos, as well as the Department of Astronomy at UT Austin. So the idea is to have a free conference. We also provide some student travel support. This to build like a community in the Southwest for the star and planet formation. So I will end my talk and take questions. Thank you.
So you began by talking about top-down planet formation with the spiral structure, and then said that probably wasn't the dominant mode. And then near the end, in some of your pictures, there were things that kind of looked like spiral arms. So since it's not the dominant mode, like how much of a role do you think it does play, and does the role depend on the type of disk?
So that's a very interesting question about spirals. In our data, we do not see a lot of spirals. But recently I've been working with mentoring a summer student. We did some like synthetic observations, try to test to see how much spirals can we recover if it's viewed by ALMA in dust continuum. But the result shows that like most of the spiral cannot be detected, because the lack of spirals in our observation could be observational bias, because it's easier to detect using gas. It has a much higher contrast, but having like a spiral inside the disk is much harder to detect. So I think we're missing a lot of spirals. And even though like there are studies showing that the disk mass is not gravitationally stable, but disk mass is very difficult to estimate. Especially we don't know of like the dust size distribution, especially kappa, the opacity. So the dust mass can actually be off by, like, it's correct within the order of magnitude. And well, since the plot I show is measured with the same ALMA band, and so the like absolute the relative positions is correct. It's just the absolute values can shift down and below by maybe a factor of few. So I think the biggest problem for the disk is the top-down approach is that it cannot produce the trend for like the giant planet occurrence rate with the metallicity. Because once your disk becomes gravitational unstable, you would just like fragment and then form giant planet. You don't expect it to be correlated with like how many dust you have. So you don't see that trend. So that's the main reason why not a leading model at the moment.
Thank you for the I have a comment and a question. My comment is like for, as far as I know, I worked with Dr. Hsieh and David Hsieh team. We are for now updating our our observations with band 8 and like the declassification idea. And as far as I see, it's like all the findings from Campus and the other teams are kind of coherent. There is some coherence, but it's just a matter of definitions. I can see because, for example, in Campus, you didn't take in account, like for example, subtle inflection points as sign of substructures. And I think the major finding in Arcajo is that they find like a Mars-sized planets can form something in the disk. So I think if we gather all the data together and like work together with some definitions, I think we could find something very interesting. And yes, I think we are also seeing that the early class 1 disks, we can see some substructures. So it's pretty nice. I can show you. And my question is like, so we now know that early class 1 disk can have substructures. We don't know yet if it's like due to planets, and we can discuss this. But do you have an idea of how could we disentangle the class 0 from 1 if there is a problem of depth and we cannot see the substructures in class 0? We don't know if it is because they don't exist or we cannot observe. But do you have an idea of how could we like
Yeah, that's a very good question. So one way to do is to do like multi-pole wavelength studies. So if you observe with different ALMA bands, then you can calculate the spectral index. And from there, you can know whether your disk is optically thick or not. If it's optically thick, then you know this is deep, you cannot really see substructure and it's due to optically thick. And so that's like one way to test it out. Or you can conduct the search of these substructures to longer wavelengths. So possibly, but like band 3, or maybe a lot of times band 3 is not enough. You probably need to see if you can push all the way to band 1 and try to see whether there's substructures. So you have to go to longer wavelengths, but at the same time, it becomes much harder because if you go to longer wavelengths, your integration times will like skyrocket.
Yes.
So that's why like that's the general direction to do if you want to know whether substructures hidden in the youngest class 0 disk and try to avoid optical depth issue. But it just generally takes a lot of ALMA time.
So if we don't have this problem of ALMA time, you think that we could disentangle.
If we don't have ALMA constraint on
We
ALMA,
accept like 100 hours, 200 hours of observation.
just go for like the band 1, the best angular resolution possible in band 1, and then just like do the whole thing, and then you will know the answer, whether it's there or not.
back on slide 3. It doesn't have to do with disks. Yes, this. Okay, so going from hot Jupiters to like the sub Neptunes, it looks like there's like a bridge there. Is that a real feature, like in like the evolutionary process of planets, or is
Yeah, okay, so that's a good observation. Here between the Jupiter and like South Neptune, there's like a gap. So that's real. Let me see. Do I have I might have a slide on. So this is known as like the photon gap. So in 2017, they plot like plot the planet size, and they found there's a gap between like super Earth and sap Neptune, and this is mostly due to like whether there's like refractories on the surface. So like for example, our Earth is actually very refractory poor. It has water, but it's not much. So the gap is like separating between like super Earths and sap Neptunes, and also between like sap Neptunes and the Jupiter's gas giants. It's a much larger gap.
I still don't know why.
Okay, let's thank Cheng-Han again.